1st of July. It's in the lecture. And the air conditioning stops in July. Hey, hi everyone. For the last day, I managed to organize a sauna for you. Spa treatment.
We're just going to take our shirts out and go to the back.
Yeah. You lose 3 layers of skin. Okay. So we're back at linear algebra. Is that linear algebra? I don't think so. Where did I go into? Oh, I went into the wrong linear course. This is linear algebra. Hey, what number lecture are we at?
Just put last.
That's true. Okay. No, I wrote it. We will start with an example of finding the representing matrix of a linear transformation. Um, I think I didn't mention something important for this. And just a quick recap for myself and for you as well. Okay, so linear transformations are basically functions which have hold two conditions, and some kind of distribution, and scalar multiplication moves out. And I mentioned a theorem. Where is it? Here. That if you have a linear transformation between two finite dimension vector spaces, then there exists a matrix such that if we multiply the coordinates by the matrix, it applies the function. So instead of applying T of V, I'm simply doing matrix multiplication by the coordinates of the vector. Okay. What I didn't say in that theorem, and I will say now before we start, fact, the columns of the representing a matrix are the coordinates of the images of the bases of the domain. Hey, Sammy. So this theorem being worded, I think it's harder to comprehend than the mathematics notation, which I'll write in a second. The I column of the representing matrix from B to C is the coordinates of T of the I member of the base B. So look at what I'm saying here. I think in the mathematics formulation it's easier to grasp. we have the matrix, the representing matrix. I told you that it exists, but first of all, I didn't prove it, but that's something else. But I also didn't tell you how to find it. So now what I'm telling you is how to find it. And I'm saying that if you want a column, to find a column of this matrix, what do? You apply the function to a vector in the base of the domain, and you take its coordinates by the base of the range of the image. Okay? And I'll show you an example as to how it looks. So, but I'll give you an algorithm basically. One algorithm to find, algorithm to calculate the representing matrix. So first, apply the function t to the vectors of the base p of the domain to calculate. It's trying to put on the air conditioning.
Doesn't work.
Yeah,
No, don't worry. If it did work, it would be on.
yeah.
How long will it?
So at 1:30, if it won't work, then we'll go to my office. That's what we agreed upon. Thomas told to make reservations for the air conditioning. They asked for his name and his phone. Calculate the coordinates of TBI and by the base C. And 3, put the result in columns, and that is the representing matrix. Thomas, if you're walking, it's like exercise, you're just getting warmer.
Yeah, I'm thinking the only panel that could be connected is this one. So like
You can open it and try, but it has only one big switch.
Instead of that one didn't work.
You can open it. Maybe I did.
I believe you. I just I just don't want to cut power there to the
Yeah, why not? That's communism. If we're hot, they should be just as hot as us.
Yes, he's the means of cooling.
Last time I checked, Israel was not a communist state.
Yeah, because you checked too late. Let's go to a kibbutz.
Depends on where you check. I think no one ever admits to being a communist, you know? They always say no.
No, we're socialist.
Yeah, that's right. Yeah. Except youth in capitalist countries, they're the only people who claim to be communists.
And they aren't even communists.
Yes, but it's cool. Okay, so we wish to calculate the representing matrix. I gave you the algorithm. I gave you an example last time, and now we will do the calculation. So try to stay with me. That's the function. The function function's input, the domain, is vectors, our vectors from the plane R squared, xy, pairs of xy. The output is our vectors in the 3-dimensional range here, R cubed. The base that we chose for the domain is this. We could have chosen any base whatsoever. The base we chose for the image is this base. We could have chose any base whatsoever in linear algebra 2, you will learn how to choose the base wisely such that the matrix will be nicer, usually diagonal. But now all these are our assumption. That's the given data, which is random. And we want to find a matrix that applies this function onto the coordinates. So what does the algorithm tells us to do? First step, apply the function to the base B. So we'll plug in 1, 1 here, and we'll plug in 1, 2 here, and we'll get vectors in R3. Second, we need to take the coordinates of these vectors according to this base. And I'll remind you, what do we do with the coordinates? They are the coefficients of the base. I will look for scalars that when I multiply this base with them, I will get t of 1, 1, and I will get t of 1, 2. Then these scalars I will write them in columns, and that would be the representing matrix. That's the idea. And now let's do it. And like I said, it is important. This very example is super important because in linear algebra 2, you will do that a lot. Right.
I mean,
Yeah.
does it have to be composed of the vectors we have already? Because like this seems to be like 1, 0, 1, 1, 0, 1, and that's it.
That's according to the standard base. If you would have taken the standard base, remind me, I will do that as an example next. It would be quite easy. But like I said, you need to be able to do it for any old base, and because sometimes for other bases the matrix becomes nicer, right? It's a better representation of the function. But for now, I chose a random base. It's definitely not the easiest one on purpose. So now let us solve the question above. So first step, t of 1, 1, that's 1, 2, 1. Look at the formula. Right, t of 1, 1 is 1, 2, 1. That's 1, 2, 1. And t of 1, 2, that's 1, 3, 2. 1, 3, 2. And I wish I'll copy all the data here. It's would be easier. So I wish to find the scalars that when I multiply the elements of C, I will get 1, 2, 1. Can you guess it? It won't be, we'll learn how to do it without guesswork, but can you guess what scalars should we multiply these in order to get 1, 2, 1?
You see, have to have one of the first one for sure.
Yes.
The problem is that if you it's minus the first one.
No.
Because like you have a -1 on the third one, you need to
Yeah.
apply it at least once, but it goes to 2.
No. And how do you make 2 into 1?
0, 5, 0, 5 for both.
Yeah. It's 1 half half, right?
Yeah.
1 half half. Because the sum of these two is 2, 0, 2, 0. And when you divide by 2, you get 0, 1, 0 plus this is 1, 2, 1. So yeah, the coordinates will be, you will see it, 1 half half. But what we should do is solve this problem in general and get the general formula to find the coordinates. and what do I mean by that? Given any old x, y, and z, we wish to find the coordinates such that a times 1, 1, 1 plus b times 0, 1, 1 plus c times 0, 1 minus 1 will be x, y, and z. We want to solve it in general, okay? So that means that is true if and only if the coordinates of x, y, and z, according to the base C, are A, B, and C. Okay, that's the main idea of coordinates, and we'll solve that system in general. Yeah.
To the Gaussian elimination we go.
Yeah, exactly, like
Uh,
always. So we have the matrix and sorry, 1, 1, 1, 0, 1, 1, 0, 1, minus 1.
It doesn't really matter if you do column or row in this case, right?
It does.
That's
It does. It's only columns. And because we're solving a system of equations, the coefficients of A are 1, 1, and 1. It's the first column.
no.
So let's do it quickly, hopefully quickly. So yeah, this is
R2
0,
minus
y
one.
minus x. This is 0, d minus x. Then we have 0 minus 2, which is minus x
y.
minus x, it goes, so it's z minus y.
And then you
Yeah, I could have for the first step take the third row and the second row out of the third row. And we divide by -2. So that's 1, and that's half of y minus half of z. And lastly, and this is 0, I, and now y minus half of y is half of y minus x plus z over 2. And altogether we found that the coordinates of x, y, z, a general vector by the base C, are x, y over 2 minus x plus z over 2, and y over 2 minus z over 2. And now that we solved it in general, we can apply it for each vector that we like. We would like to find the coordinates for these two. So now we simply plug it in and get it immediately. So if you follow, what would be the coordinates of 1, 2, 1?
1 1 minus 1 0 plus
1 half half. Do you remember, Thomas? Because we said it before. I didn't plug it in yet. I noted this before, but let's make sure it's true. So x is 1, so it's -1. Y is 2, so 2 over 2 is 1 minus 1, that's 0, plus z over 2, that's half. And here we have y over 2, which is 1, minus z over 2, which is half, so it's half. So we really found the scalars that we guessed before, but now we have an algorithm as to how to find them in general. Yes, Thomas.
I'll be honest, I have no idea what's going on. Your C is the base of the output
Yes,
and B is the base of the input.
yes.
So what we found is how to represent
The base of the output. By the base of the output, yes.
Yeah, but if we have the base of the output, so what we found is how to represent the output in R3 based on the base of the output.
Yeah.
Okay.
Yeah. Here we found how to represent any vector in R3, and now we are applying it specifically to the output of the function. So this has nothing to do with the function. You don't see t here at all. Here we're simply asking how to represent a vector of R3 using this base. So that's a general ability. Now we are applying it specifically, and I'll write it as well, to the output of 1, 1, right? So that's from the base B, right? We plug it into the function, and then we are calculating the coordinates according to the base of the range. Okay, and that is exactly what's written in the algorithm. Okay, you can read it again. We're applying the function to the vectors of the base B of the domain. Then we're calculating the coordinates of the outputs according to the base C. And the last step is no step. It's simply writing it in columns. That's nothing.
We don't have to find how to represent the input based on B.
No, we don't. It's not a part of the algorithm. You don't need to. Okay, you just need to apply the function to the base of B. It is there, right? We're not ignoring the base of B, but you don't need to find representation according to B. Okay, that's
left as an exercise for the user.
Yeah, but what I mean, it's from the proof. That's the fact. These are the columns of the representing matrix. Okay, that's not my choice. It's unique, right? So these are the columns and no others. So that's not my choice. That's math. I didn't prove it to you. That's true, but it's not my choice anyway. And then T of 1, 2, according to C, is 1, 3, 2, according to C. And now we plug it in. 1, 3, 2. So the first you do that 1, and now y is 3. 3 over 2 minus 1 is half plus 1. So it's 3 over 2. And the last one is y over 2, which is 3 over 2 minus 1. That's half. So altogether, the representing matrix from B to C is 1 half 1 3 over 2 1 over 2. And
This is because you calculated all the vectors in the base of B.
I followed the algorithm. First step, I applied T to the base of B. Second step is find the coordinates. Third step is simply writing it in columns.
Okay.
Put the results in the columns, and that is what is the representing matrix. And I wonder if I'll enter it into ChatGPT, will it be able to solve it? I never did that kind of exercise using the chat. Let's make sure.
I'm putting my money off it talking about the eigenvector for something.
Step 1, apply T to each basis vector in B. It listens to me. Step 2, express T of Vi in coordinates relative to the basis C. Exactly the steps I told you. and he got to the same number, by the way. Final step, write the matrix. Each column is the coordinates of TVI to C, exactly as I explained, and even exactly the same result we got together. Okay, that is impressive. And maybe he listens to me. Okay. So we have this new ability of finding the representative matrix. And let's do an example on the example. And say, what is T of 0, 1? So simply calculating it, it's easy. We plug it into the formula here. So what is T of 0, 1? That's 0, 1, 1. Do you agree? 0, 1, 1. Okay. Now let's look at the equivalent equation using the coordinates. So instead of T, we will write the representing matrix of T. Instead of 0, 1, what should we write here?
Based on the base of B.
Exactly, the coordinates of 0, 1 based on B. And what do we expect to get here? The coordinates of 0, 1, 1 in the base C. That is what is supposed to happen. And now we're just verifying that indeed it works. Okay, that's just a verification. The math promises us that it's true, but we wish to work it out because we know the matrix. The matrix is this. We can find the coordinates by C because we have a formula up there. The only thing we'll have to do is to find the coordinates of 0, 1 by B. That we'll do using guesswork. It's rather easy. Okay?
My favorite
Instead of calculating it. We can calculate it by the way we learn, but here it's easy. I chose the vector in advance, so it will be easy. So indeed, the matrix is this times. So what are the coordinates of 0, 1? Look at the base B. How can you get 0, 1 from these two?
Minus 1, 1.
Exactly, minus 1, 1. Okay, minus 1 the first times the first plus the second. The first one is eliminated. Minus 1 plus 2 is 1. So that's the scalars here. The coefficients are minus 1 and 1. So that's minus 1, 1. And we are supposed to get what's 0, 1, 1. We need to apply it into these formulas. 0, 1, 1. So that's 0, 1, 1. And that's 0, 1, 1. That's half plus half. That's 1. And 0. Another interesting example here. Look at this. What are the coefficients here? It's 0, 1, and 0. Why am I saying this is interesting? Look at the base C. Who do you recognize within C? That's what a coincidence. I didn't.
0, 1, 1.
0, 1, 1 is here, right? So the coefficients are really easy. If you wish to create 0, 1, 1, simply multiply this vector by 1 and the others by 0. That's exactly what we got here. So it makes sense. And finally, you can do the multiplication. 1, 1 times minus 1, 1. That's 0. Half, a minus half plus 3 over 2, that's 1. And half, that's 0. So the equation holds. Mathematics lives to see another day. And it was right yet again. Yes.
This is probably beyond what we are talking about, but if we found how to get the input by the base of B, and we find how to get the output by the base of C, can we multiply them together and just get like one function that goes from one end to the other?
No, because what would be the function? What would be the multiplication?
So you have
You have a coordinate system here and a coordinate system here. What happens if you multiply the coefficients? You get nothing, right? It's meaningless. It has nothing to do with the function. Remember that an important step was applying the function, right? What you claim has nothing to do with the actual function.
Mhm.
Okay?
So you have to apply one multiplication to get from R2 to B, and then from B to C, and then from C to R3.
But again, you don't need to calculate the coordinates according to B because the matrix, their columns is just applying the functions actually to B, looking at the vectors and find their coordinates according to C. You don't have to calculate the coordinates using B in order to find a function that does something to these coordinates. Maybe surprising, but that's the fact. There is a reason for why it's happening. But that's just the way it is. Theorem. What happens? Oh, I'll give you that at first. Given two linear functions, t from B to W, and S from W to U, and given B, C, and D, and bases, and assume, I'll write some words, and assume B, C, and D are ordered bases for V, W, and U. Then, if you multiply the matrix of S from C to D by the matrix of T from B to C, what do you suppose we will get?
Shouldn't it be the other way around?
No.
The composite function from B to U.
The matrix of the composite function S over T, and now does it make sense? It's the right order, right? Because T acts first, S acts the second. T goes from V to W, and then S continues from W to U. So the multiplication of matrices is exactly representing the composition of the function. And from where to where?
B to U.
You need the only bases, U is not
B
a
and
base. From B to D. Yes, exactly right.
The linear function is always applied from the left.
Yes. What do you mean? The linear function is a function. It doesn't apply from left or right. When you multiply the matrix, yes, you only multiply from the left. And that's exactly the formula. Where is it? Here. You see, it's from the left. That's it. If you wanted to, you could have had all the, well, I'm not sure if you could have had it from the right, to be honest. But yeah, the formula is from the left. When you apply the matrix, it's from the left. And therefore, this is rather easy to prove and is left as an exercise for the reader. And a specific interesting example, interesting example is as such. Take a given t from V to V, a linear function. It will be called in linear 2 operator, since it is from a space on to itself. For this course, it's not very interesting, but in linear algebra 2, the lecturer might say a lot of times operator, and then you might say, we never learned about operators, but it's just a name. An operator is a linear function specifically from a space to itself. So it's not really interesting, but it's used quite often. So any case, like I said, it's a specific interesting example. So if I have an operator, meaning a linear function from a space to itself, and consider the bases C, B, C, let me think for a second, B and C. Consider the bases B and C for V. So suppose that I have the representing matrix from B to B, and I want the representing matrix from C to C. So this is not true yet. This is not equal. These will be two different matrices. But the question is how to change from one to the other. So the only tool we learn to do any change is composition. But if I do composition, then the function will be composed, and that's not what I want. Which function, when you compose it, does not change anything?
The identity.
Exactly. So what we do here, we use the identity, the matrix that represent the identity on both sides, and we simply fix the bases. What do I mean? You start with B, and the output is C, and here you get C and output B. And that is simply a specific case of that, because you have to have that the basis that comes out is the basis that goes in, the basis that comes out, it's the basis that goes in. Now you can apply the composition, and the composition of I, Ti is simply T. So that is a very important example for linear 2, but it's a specific case of the theorem I just mentioned. Yes, Thomas?
How can you have an identity between bases?
It's the same. What do you mean?
Like let's say you have.
You're speaking about this matrix?
Yeah.
Let's look at it for a second. Note. If you take this matrix and you multiply it by the coordinates of some vector V according to C, what will the output be?
In theory, B according to B.
Exactly, V according to B. So that means that this matrix is not the identity matrix. It does something, it changed something, it changes the coordinates. So there is such a matrix. And how to find it, we learned. right? We apply the identity function to the base of B. We take the coordinates according to the base of C, sorry. We take the coordinates according to the base of B, and we put it in columns. It's just a specific example of the algorithm we learned above, right? Apply the function on the base of the domain, find the coordinates according to the base of the range, and then you put it in columns.
Yeah, but what does it mean? Like, if you go from R2 to R3, what is the identity in this case?
No, it couldn't be. That's why it's an operator. It's from V to V.
Ah, okay.
That's why the word operator is so important, because it's only relevant when you have the same space in the domain and in the range. If you have different vectors, then you couldn't say from B to B. It doesn't make sense at all. Okay? That's why I say it was specific. But it is general in the sense that in linear algebra 2, we will mostly work with this example. But the general story is from any V to U, and then B and C are different bases. They must be. Any questions so far? Another theorem, I think the last that we'll have in representing matrices, and then we'll learn about kernel and image. So another theorem, given a linear function t from V to W, and given bases B and C, T is invertible. When is a function invertible? That's not linear algebra.
When
That's
it's
discrete math.
injective and subjective.
Surjective.
Subjective.
Yeah, subjective. It's subjective. It's subjective. It's invertible for me. It's okay. Yes. So T is invertible if it's onto and one-to-one, surjective and injective. That's from discrete mathematics. But what I taught you in linear algebra is that linear functions are matrices. So how do you think I will finish this sentence? I don't wish to go to the discrete mathematics way. I wish to go to the linear algebra way.
Three variables.
No, but it's not a matrix yet. T is invertible if and only if its matrix is invertible. That's all. If and only if the matrix T from B to C, and it doesn't matter which basis you choose, is invertible. And that's like you said, finding whether it's invertible is using Gauss elimination, like everything. And also, in that case, the matrix that represents the inverse function from C to B is the inverse of the matrix. All these theorems together simply proves, I don't know if prove is the word, in science, when you do an experiment and it follows the theory, what's the word for it?
What?
In
Hypothesis?
science, what?
Hypothesis.
No, but when you do an experiment and it doesn't contradict your hypothesis.
It confirms.
Confirms, I think. Confirms, I think.
Consistent is good as well.
No, but I think confirms, because that's the word I was looking for in Hebrew, meoshesh. It confirms. I think that's the word I was looking for. All these theorems confirm my assertion that linear functions are just matrices. You see that everything I wish to say about functions translates exactly to what I know about matrices. You want to find the inverse function, just find the inverse matrix. It's the same. It's represented. Okay, so that's what I'm saying. The multiplication of matrices is the composition. So all these theorems confirms my assertion that linear functions are matrices, basically. Okay. And again, if you have an exercise of finding the inverse function, what you can do is find the representing matrix, which we just learned, and then invert it using Gauss elimination. Okay, that's why most of the course is in the language of matrices, but what we're actually interested in are the linear functions. Okay. And by the way, that is objectionable because especially I think in computer science, because the language of matrices is easier, many is the times that you just speak about matrices anyway. If you wish to do a rotation, that's a function, right? But you take a rotation matrix that does it, and a lot of the time you simply stay in the language of matrices because it's easier. But here we'll learn them both. Any question so far? Okay. I will do a quick run through. I know at least one theorem that I skipped, but it's rather trivial. But I wish to make sure I didn't skip anything else. And then we'll go to the final subject. So we're at linear algebra. This I skipped, but I will teach today. That was knowingly. These two, I'm not sure if I'll manage to prove, but I'll try to show them. This I showed you. These are the coordinates. That's what I did. That's the theorem I've shown you. Yeah, so here, these are the things I told you I skipped. It's also true for the addition of functions and multiplying by a scalar. The matrix of the sum of functions is the sum of the matrices, and multiplication of scalar as well. That's the inverse thing. And this I showed you a second ago. Yes, and that's it. Okay, so I didn't forget anything. Great. Okay. So, last subjects, kernel and image of linear functions. So the image of the function you already learned in discrete mathematics, it's the same here. Kernel is supposed to be a new thing. I'll remind you of it anyway. So definition, given a linear transformation or linear function t from V to W, and we define first the kernel of T, for short ker T. What does the word kernel tell you? For Hebrew-speaking people, they usually are not even familiar with the word kernel.
It's like a grain, like a
It's the core of something.
Yeah, it's the core. It's the core of something.
popcorn kernel.
Yeah.
But it's. I think it's a bit confusing as to why it's called the core. And that's it. I don't have a lot to say about it other than that. But it is the core in some sense. It is the core in some sense. So the kernel of T are all the vectors from the domain such that they are sent to 0. Okay, the kernel is the set of all vectors being nullified, being sent to zero. Why is that the core? We will see later that it measures just how much T repeats itself. As the core is bigger, more things are going to zero, and that means that T sends more things to the same places and repeats itself. As the kernel is smaller, that means that T is more one-to-one. It does not repeat itself. I will formulate it as an accurate theorem in a while. Okay, but that's the reason the kernel is important. It measures just how much the function is one-to-one. Okay. The image of the function T is just as in the discrete mathematics. It's all of the TV such that V is from the domain. So where does the image resides? The kernel, as we said, is within the domain because it's a subset of the domain. What about the image?
In W?
It's in W, right? Because it's all of the images. You apply T to all of the vectors of the domain, and you consider what came out. And that's the very same definition as in discrete mathematics. Another way to describe it, an equivalent way to describe it, it's all of the W within W, such that there exists a V in V, such that TV is W. Okay, so these two definitions are equivalent. It is exactly the same set. This is a set of all elements of the range, which actually have makor, a source element. So without proof, as an exercise, HW, oh, it is HW, not HW. So HW, prove these are subspaces. They are not just subsets, these are subspaces. The kernel is a vector space and the image is a vector space. Okay. Using the tools we learned about subspaces not so long ago.
What? Why would the image not be a subspace? Isn't the image just W?
No, the image is not W. It's all the vectors that. Let's do a quick example. Exactly.
All of the vectors we can get to on
Yeah,
the
that's the
function.
difference between image and range, right? Look at a quick example. Say T is from R squared to R squared, such that Txy is XX. I've tried to choose an easy enough example that you can see the kernel and the image easily. What is the image of T? It's the span of 1, 1. Do you agree, Thomas?
Yeah.
Yeah, it's not all of W. All of the vectors that comes out of the functions are of the form XX. Agreed? What is the kernel?
Kernel is 0, 0.
Not
know.
only. 0, 0 is always in the
0,
kernel.
0, A, right?
No. Oh, wait, yes, you're right. And 0A. Span of 0, 1. Yes. Okay. So all of the vectors of the type 0 something goes to 0, and nothing else, because X must be 0, and Y could be whatever, and the image is 1, 1. Okay. Let's do another example, another easy example, but not of an operator, but of a function between two different vector spaces. So T of xy would be x minus y, 0, 0. Okay. So first of all, what would be the image of this function? Who can tell me
The image of
this function?
it's 1 0, the span of 1 0 0.
Yes, exactly. The span of 1, 0, 0. Because everything that comes out of this function is of the type something 0, 0. So that's the image. What about the kernel? What is being sent to 0, 0, 0?
The span of 1 1.
Span of 1, 1. Because when x equals y, then you get 0. Agreed? So, I think that is a good time for us to take our break until 2:15.
What are we going to do with staying here?
I'm not sure. Is it still hot?
I mean, it's not unsustainable. It's not great either.
I leave it up to you. Do you wish to move to my office where there might be an air conditioning or stay here?
I'm happy to stay here.
Stay here?
Fine. Also, if we go to our office 1 second later, they're going to call me, hey, we came to fix.
Uh, So we defined the kernel and the image of a function, linear function. And now we're going to see the connection between this and matrices like always. So an important example. So recall that given a matrix A from a set of all matrices of size m by n, one can define the what I think I called it matrix function. I'm not sure, but I'll remind you the definition anyway. And the matrix function TA from Fn to Fm by the matrix function. What does it do? It simply multiply any vector by the matrix. And that's a linear function. We've seen it last time when we studied about linear functions. What we wish to study, what are the kernel and image of this function. And this is the quite general case because every linear function is a multiplication by the representing matrix, right? But you need to go to the coordinates for that. But we wish to know what are the kernel and images of such functions and what does it have to do with the matrix. So let's see. First of all, what is the kernel of this function? It's the set of all vectors V such that they are being sent to 0. But the function is simply multiplying by the matrix. So it's the set of all V such that AV is 0. And what did we call that set?
The kernel of A.
In A, we didn't call it kernel.
The null space.
The null space, exactly. Okay, so kernel is simply the null space. It's not a new thing. It's the same thing, and I say it over and over again. It's only different names for the same things we were studying from the second chapter of this course was a linear system of equations, and we had the homogeneous system of equations. That's exactly the null space. That's exactly the kernel of a linear transformation. We studied it from the day 1 or day 2, but still we need to be able to do the translation between the two. So the kernel is exactly the null space. The image is a bit more subtle. So what is the image? What is the image of this function? So it's all of the TAV such that V comes from the domain, which is all of the A times V such that V comes from the domain. This is a bit more surprising if you don't know it ahead. What is this? What happens when you multiply a matrix by a vector?
You get another vector.
Yes, that's bravo, Thomas. You get something. It's the set of some things.
It's the general solution for something.
No, it's not a solution. The solution is the null space.
Hmm.
So that is a bit more surprising. and I'll try to help you to get it yourself. Write A by its columns. Meaning the first column is V1, and the last column is Vn. Okay. Now multiply it. AV is this matrix, this is A, and instead of V, I will write the scalars that comprise it. Xn. Do you recall as to how to calculate this?
The sum of all of the elements in V1 times X1.
X1 times V1 plus Xn times Vn. Okay, that's the calculation of the matrix multiplication by columns. I think we talked about it only in the
Practice.
yeah, only in the connection with the you asked me about it from the homework. You had such questions. Okay, so even if you've never seen it before, this is a fact. Okay, what does it mean? But now we can look at it from a more mature perspective. What is that? What would you call, well, not this. What would you call this sum here? Scalar time vector plus a scalar time vector.
Wait, this is for each row, right?
It's all together because V1 is a vector, it's a column.
Yeah, but it's not, the
the-
output is another vector.
Yeah, V1 is a vector. When you sum up vectors, you remain with a vector. Look,
Okay, yeah.
I'll show you a quick example just so you see that it's true. It's not the interesting part, I think, but it is important that you see it in your eyes. So suppose this is, I don't know, 1, 2, 3, and this is 4, 5, 6. If we multiply it by 1 minus 1, 1, then it's minus 1 times the first column plus 1 time the second column, which is 3, 3, 3. Okay, so what's written here? That's that. This is this, and that is the final result. And it's true, it's a theorem, okay? But again, now maybe it will be more helpful when you see it. Scalar times vector plus a scalar time vector, and so on. What do we call such a thing?
Combination.
A linear combination, right? And you are allowed to choose each scalars you want, right? You go over all list of all list of vectors, all list of scalars. So it's a linear combination of what?
Basic
No, what are V1 to Vn? Vn?
vectors of A,
What vectors of A?
column vector.
The columns of A, exactly. That's a linear combination. That is just a linear combination of the columns of A. That was my main point. So the answer finally,
The image is the base of the column space.
it's the column space. It's not the base, it's the column space, exactly. And I'll just write that's an explanation. So yeah, the kernel of the linear transformation is the null space. and the image of the linear transformation is the column space. So again, we're not, we learned all this stuff about matrices, and now we see them with linear transformation.
The kernel is a subset of the image.
No, why?
Uh,
Null space is not part of the column space in general.
no, yeah.
It doesn't even have to be on the same size.
Oh, yeah.
These are two different spaces. I think you're confusing with the homework you had,
Yeah.
at which they gave you as an assumption that one is included within the other within the specific example, and it was an operator. It was a square matrix. The size of the number of the rows was equal to the number of the columns, then it makes sense. But in general, they don't have to be even in the same size.
Yeah, no, but there's a relation between the kernel and the image in this in general, no?
No,
No.
just dimension-wise.
Dimension wise.
Because the dimension of the null space is the number of free variables.
So
The
it's-
dimension of the column space is the rank of the matrix, is the number of bounded variables. And their sum, that's the connection, and I'll write it as a theorem in a second. Their sum is the dimension, is the number of variables altogether, which is the dimension of the domain. So now I'll write it as a theorem. And given a linear function t from V to W such that the image such that V is finitely generated, such that it has a dimension, such that V is finitely generated, meaning it has a dimension. Then the dimension of the kernel plus the dimension of the image is equal to the dimension of the domain. And within matrices, it's, by the way, it's a way to prove it. And that's why I won't prove because I don't have much time, but that's an excuse, I would say, that you can use our knowledge of matrices to deduce it, because the kernel is the null space, it's the number of free variables, the image is the column space, it's the number of bounded variables, and together it's the number of columns altogether, which is the dimension of V. Okay. So in general, that's the connection between the two. And now a small theorem, which we will prove, theorem, and given a linear function t from V to W, then t is injective one-to-one if and only if the dimension of the kernel is 0. Note the dimension of the vector space is 0 if and only if the kernel itself is only the 0 vector. So we claim here that we can know whether the function is injective one-to-one or not, just by looking at the image of the kernel. And if you calculate the representing matrix, it's simply finding the null space, which is Gauss elimination. In discrete mathematics, proving that the function is injective could have been hard, but in linear algebra, it all comes down to Gauss elimination, and then you figure it out. And this theorem I will prove. Yes, Thomas.
For the injective function, linear functions are also surjective.
So let's consider what Thomas is asked. It's a good question. He says, let's think of an injective function. That means that the kernel, the dimension of the kernel is 0, right?
Oh, wait.
So that means that the dimension of the image is the dimension of the domain. Does it force it to be surjective? Only if the domain and the range has the same image. And then the answer will be yes. If the domain and the range has the same image, then the function is invertible if and only if it's injective. But if the domain and the range has different dimension, then it won't be.
So I realized.
But there is a strong connection. By knowing all of the dimensions and knowing if the function is injective or not, you can immediately know whether it's surjective or not.
So I realized
That's the point of the whole thing, yeah.
I realized the issue is that I was thinking in square matrices.
Yeah, exactly.
So-
So in square matrices, it's true. The matrix is invertible if and only if the null space is only 0.
But if you have more columns than rows, then you can get
Yeah,
it
then
other
no,
ways.
exactly. Okay. So yes, so that's what's going on here exactly. So proof. This time I wish to prove it. So it's a bidirectional proposition claim. So we need to prove both directions. Let's start from the first. First, let us assume that T is surjective. We need to prove that the kernel is only 0. The fact that 0 is there is obvious since the kernel is a subspace. So assume by contradiction that there exists some vector v which is not 0 within the kernel. Oops, there exists some vector which is not 0 within the kernel. What does it say that the vector is within the kernel? Since V is a member, an element of the kernel of T, then what?
A, B.
No, there is no A here, but
So the TV
TV is equal 0, right? What's the problem with that? And by the way, I made a mistake here. I assumed that T is surjective and I meant injective. 1-to-1.
Injective.
What does it mean that a function is injective?
That there's only one way to solve. That there's only one output for each input.
No,
No,
that's every function.
There's no two different inputs that give the same output.
Exactly.
And we know that the 0 vector will give 0 in the
Exactly. But also T of 0 equals 0. Looks like a smiley. Let's write T of 0v and this is 0w. This is also the 0 of w. Yes. So T of v is the 0 of w, and also T of 0 is the 0 of w, in contradiction to T being injective. Yes.
Does this work for every case because the function is linear and
Yes.
because
Well, this is the obvious direction. Obviously, not for linear function, for any function. Because t is linear, then t of 0 is 0. That won't be true for any function. So yeah, even in this direction, I use the linearity. But on the other direction, I use it more.
yeah, no, I mean, given that it's linear, there's no way there's two different b's such that tb is equal to 1 and this doesn't happen. That's what I mean. Because like we're saying because bt equals 0 and there's another 0, it's fine, but because it's linear, it's for any, if there exists such b such that t1 bw such that bt equals 1 and tw equals 1, then this also happens.
I think if I get you correctly, I think, yeah, that's the other direction. And you'll see it in the proof, and then you tell me that if that's what you meant. But I think the answer is yes. In the other direction, now assume that the kernel is only 0. And we wish to prove, and we will prove that T is injective. So how do I prove that the function is injective? Assume TV1 equals TV2. What do we need to prove? That V1 equals V2. Thomas, look at this. Is this what you meant?
Yeah.
What's the next step?
We use matrix multiplication.
Kind of, but it's not matrix. But what do we do here? Try to look at this and say what would be the next step here.
So by contradiction that it's not?
No. I think it's what you said. I'll help you do the first step. So TV1 minus TV2 equals 0, right? But what is TV1 minus TV2?
T of B1 minus B2.
Exactly, that goes to 0. That's due to the linearity.
We assume that
so V1 minus V2, where does it lie?
0.
It lies within the kernel, which is only 0 by our assumption. Therefore, V1 minus V2 is equal to 0. It's the only vector in the kernel. That's why V1 equals V2. I think that's what you said, but I'm not sure.
I mean, not directly, but it falls from this, so it's fine.
Yeah. Just you keep saying matrix multiplication. We look at it as if it was matrix multiplication, but it's not actually multiplication. But the linearity allows us to do distribution and whatnot in order to look at it as if it was a multiplication by matrix.
Okay.
Any questions so far? Let me show you a cool example. A cool example. Can you think of a function y calculus such that y prime equals y
E to the
e to the x? Yes, y equals e to the x. Agreed? That is not yet the cool thing. And how about y prime equals 2 times y?
X.
E to the 2x. Okay? Now, can you think of a function? So far, it has nothing to do with linear algebra. But wait a few seconds.
Calculus.
Can you think of a function y such that the second derivative of y minus 3y prime plus 2y equals 0?
Of course.
Yeah.
Yeah.
It's differential equations.
So first of all, yeah, that's a differential equation. That's true.
It's probably going to be it's either e something or cosine something, right?
Did you learn?
Yeah.
Forget that you learned differential equations. That is true, but I wish to show the connection to linear algebra. Differential equations by itself is not the interesting part. The interesting part for me is that the way to solve it is to look at linear functions. And you will see it in a bit. What does that remind you of?
Quadratic.
Quadratic equation, right? That's the correct answer. That reminds us of quadratic equations, but it is not, right? You can't say y minus 1 times y minus 2 equals y, the second derivative, right? Do you agree that what I wrote here is nonsense, right? That's not true, but it looks like it. Consider the linear transformation D that sends each function to its derivative. I've shown you this in a former class. This is a linear function indeed, because the derivative of a sum is the sum of the derivatives, and scalars comes out. So we can write, instead of y, the second derivative of y, we can say that we differentiated y twice, right? I applied d, and then I applied d again. I will talk about this notation a bit more. What does it even mean, d squared? Usually, when we use the notation squared, we mean something multiplied by itself. Like for a matrix, a squared is a times a, right? But d is a function. How do we apply a function? Well, how do we don't multiply a function. D squared means d composed on itself. But because linear functions acts exactly like matrices, it follows multiplication rules, and we have a distribution which we will use, right? So it's d squared y minus 3 times dy plus, what would be the function here that applies to y?
IY.
IY, exactly. It's the identity plus 2 times the identity y equals 0. Okay. And now we can say it's d squared minus 3d plus 2i times y equals 0. So we look at the operations that were applied to y, and we get this. And this is definitely a quadratic function. We can say that it's d minus I times d minus 2i times y equals 0. Because linear functions work like matrix multiplication, we can use the distribution law, and we get d times d, or decomposition d, which is d squared, d times the identity, which is d, and so forth, and we get this. So we can, and that's a, I won't, okay. Therefore, if d minus 2iy equals 0, then y is a solution. And since d minus I times d minus 2i equals d minus 2i times d minus I, you're welcome to check it, but in this case it's commutative, then also if d minus I y equals 0 gives a solution. So now look at these two. What is d minus 2i of y? What's dy? What's d of y?
You mean y, the derivative of y?
Yeah, y prime
Right.
minus 2y equals 0. But that you solved easily. What does it mean that y prime equals 2y? What is the solution? E to the 2x, right? And if we have d minus I y equals 0, this means that y prime minus y equals 0, y prime equals y, that gives us e to the x. So the two solutions to the problem that we found are e to the x and e to the 2x. And now let's put this equation into Wolfram alpha and ask it to solve it. And you find that the solutions are indeed e to the x and e to the 2x. But what would you call this? C1 times e to the x plus
Linear
c2.
combination.
It's a linear combination. Why? Because the kernel and the kernel is a vector space.
Why is that linear combination?
That's the definition of linear combination, right? It's scalars times a vector. The vectors here are the functions.
E to the x times
Yeah, the set of functions are vectors as well, right? They have addition, multiplication by a scalar, and all the good.
I'm trying to visualize that. I'm finding it very
You're
difficult.
not able to visualize it. Why? But because when you say you're trying to visualize it, it means that you're assuming that vectors are only geometrical objects, but they're not. They're also algebraic objects. You cannot visualize it. You cannot even visualize a four-dimensional vector. This is an infinite dimensional vector. You're
Right,
not
because they're
supposed to be
they're
able.
infinite inputs.
Yeah,
Okay,
yeah.
okay.
So you're not supposed to be able to visualize it geometrically, but algebraically, it's a scalar times a vector plus a scalar times a vector, and that's why I like this example. I call it a cool example because you see how the algebraic tools we learned in linear algebra helps us solve problems that has nothing. You would think they have nothing to do with linear algebra. It seems calculus, differential equations, but the tools, the kernel, and the linear combination, and the fact that linear transformation works like matrices, multiplications, allows us to actually solve this. And by the way, when you said it's cosine and sine as well, do you know why?
Because e to the pi is.
Yeah, exactly, because of Euler. Because the roots of the quadratic equation could be complex, and then you get cosine and sine. Yeah. So yes.
The way you did that compared to the way I did that in high school is disgusting. Like this is like a 20-mark question. Like, and you just did it like that.
Yeah.
Can you go through the calculations again, please?
Yeah. The main thing here is
Why do you do 2IY?
I is the identity.
But
Because
why do you need
the
that?
original expression was 2y.
So
But I want to take y out as a common factor. So I have I here. Look at it with matrices, for example. Another example.
wait.
Say
No, that's
look at this for a second, Sammy. Say in matrices you have AV minus V. How can you take V as a common factor out of this?
But just taking it out. A minus
A minus
A.
I.
You could have let me answer. I wouldn't have.
But the answer was there
Yeah,
from
okay,
the get-go,
okay,
right?
yeah.
Because you can't, but I thought that in matrices it will seem more obvious because you can naturally you would like to say one,
Yeah.
right? But it's not allowed because this is a matrix and one is a scalar. The correct way to take it, to leave it here, is the identity element, which is I. And in functions, it's the identity function. So that's the reason I wrote I there.
Because we want it to be in
Yeah.
matrix form. Okay.
But it is rather quick, right? The course is not about linear ordinary differential equations. I just wanted to show you quickly how do you apply linear algebra to other subjects, and then think of students like in engineering, they were taught linear algebra in the first semester. They have only one course in linear algebra, which is absurd, but nevertheless. And then the second semester, I taught them ODE, differential equations. And and once I said, now D is a linear function, they all went, we thought we were through with linear algebra. And you're never done with linear algebra. In engineering, more than computer science, but in computer science as well, you use linear algebra all the time. Differential equations you won't see, but linear algebra, it's everything.
No, we're never going to do differential equations.
No, in computer science.
There are no courses that do differential
Maybe as a
Optional.
option course, but not in the program.
Mandatory, okay.
Yeah. I'll tell you why it makes it's absurd and it's horrible, but why it makes sense. Okay. Who invented a quick history lesson like I like? Who invented a calculus?
Isaac Newton and Leibniz.
Newton, yeah, let's just say Newton for sake of argument. So Newton, why did he invent calculus?
Because he had a problem to solve, and
Yeah, but within physics. So what?
Gravity.
why
His
the
law, his second law of Newton is F equals ma, right? Force equals the mass times acceleration. But what is acceleration?
The derivative.
It's the
Space.
second derivative of the placement, right? So in order to know what is no, let's do an example. It has nothing to do with this course, to be honest, but whatever. I don't care.
We're short on time.
I don't care. But we're short on time. Yeah, no, whatever. Because sometimes you don't want to start something new because you're short on time, so you have extra time. No, but again, I think the universities became much too obsessed with syllabus than actual learning, right? Because say, oh, it's not in the syllabus, then we'll never talk about it. But it so happens that students finish computer science without ever knowing why calculus was invented. It's absurd. So let me give you an example. What is the acceleration on a free fall? It's a bit of physics.
Gravity.
9.8.
It's the G, right? What is the by the way, if you drop a feather and a bowling ball, which one will arrive first to Earth? It's not a trick question at
bowling,
first, but the bowling ball, right? But if you took all the air out of the room, a vacuum chamber, and you drop a bowling ball and a feather, who will drop first?
Both at the same time.
Yeah, do you know it? Have you seen the experiment?
Gravity,
show you.
gravity affects all objects at the same rate.
There is a beautiful video about it.
Yeah,
A feather from BBC.
yeah.
A feather and a bowling ball.
In space.
No, it doesn't need to be in space. In this case, it's in air, but because the
Oh,
distance
it's
is
just
so
a vacuum.
low. No, it's not in vacuum. It's in air,
It's
but
in vacuum. No, it is in vacuum. The air resistance is the problem. It's in vacuum.
at low enough.
Yeah, almost vacuum. So first of all, this is with air. With air, the feathers hardly even came to the ground, right?
Going at like 100 frames per minute.
1 frame per second.
Exactly at the same time. You see it? Amazing.
Oh, is it slow on purpose?
No, it's the quality of the.
Okay, so that is a nice thing. And what does it have to do with what I'm telling you? What is the force applied to the object? What is gravity? What is the force of gravity? Does anyone know?
What do you mean? What is the force?
What
the
does it
vacuum.
equal to?
9.8.
But that's not the force. G is 9.82. But what is the force that being applied to an object? It's
Oh,
m times g. It ends times g.
yeah.
So m times g, that's F, equals m times a. What happens to the mass? That's mathematics. What happens to m?
Yeah, it cancels out.
It cancels out. That's with no air resistance. It simply cancels out. If there was air resistance, then the air resistance is not does not rely on the mass. It relies a lot about the shape of the element. So then it won't cancel out. But G equals A. Now, what is A? A is the second derivative of the height, right? So now that's a calculus question, but if the second derivative is a constant, what does it mean about the first derivative?
But it's a linear equation.
Yeah, so when we do an integral, so y prime is g times t plus some constant. And what is y itself?
Uh,
GT squared plus.
Half half of gt squared plus c1t plus c2, which whoever learned physics know this is the equation for motion with the constant acceleration. So my point is that after Newton invented his laws, in order to find the function of the motion or the placement, he needed to solve differential equations. And that's why he invented calculus to answer such questions. So we study calculus without ever having learned why do we study calculus, which is a bit weird. So just to finish my thought, so why do engineers study differential equations and computer science guys do not? Because engineers study physics as well. And in order to study physics, you have to know linear equations. But computer science guys doesn't study physics as a part of the degree, and that's why they skip it. But it's ignorance not to know this, sadly. But yeah, that's life. Okay, so that was not so
Short tangent.
yeah, has nothing to do with the course. Has nothing to do with the course.
Got everything to do with everything.
Yeah, no, but I wanted to say. Okay. This does. This does, because this shows how you use linear algebra in many different cases. Okay. Now, next, we return to our scheduled programmings. And we know that a function is surjective if and only if the image is equal to the range of the function, i.e., the linear function from V to W is onto or surjective if and only if the image of D is actually the whole of W. Does that make sense? And that is true if and only if the dimension of the image is equal to the dimension of W, since the image is a subspace of W. So we learned that if we have a subspace of the same dimension, it's the whole space. So both surjective and injective properties were reduced to a dimension question. A dimension about the kernel, which is the null space, and a question about the dimension of the image, which is the column space. So if you know how to do Gauss elimination to a matrix, you know how to answer all these questions. You'll find the matrix of the representing matrix, and then you find its rank, which gives you both the column space and the null space dimension together. Just the number of free variables versus bounded variables. And then you get all of it together. Then, for instance, example, say we have a linear function t from r cubed to r 3. From R squared to R cubed, sorry. Could it be invertible?
No.
So hold your horses. If we look at it from cardinality point of view, the answer is yes, because the cardinality of R squared and R cubed are both Aleph. Study cardinality in the. But from cardinality point of view, there's no problem. There exists such a function that is invertible from R2 to R3. However, we are speaking about a linear function, right? So, Thomas, you said no. Why?
Because the matrix necessary would need to be square, and you.
Oh, that's nice. That's a nice answer. Thomas says, since the representing the only invertible matrices are the square matrices, and the matrix here will be 3 by 2. Yeah, you are correct. And by the way, I told you that we will see why invertible matrices are only squares. So now let's forget for a second that you know this rule. We're more or less proving it. Okay, so forget the fact that in order to be invertible, a matrix has to be a square. We will see now why is that the case, okay? So give me another answer. Why couldn't it be invertible?
Because the image.
If it was, let's do it slowly. If it was, then T is both injective and surjective. Do you agree about that?
Yes.
What does it tell us about the dimensions? Since it's injective, the dimension of the kernel, what is it?
0.
Is 0. Since it is surjective, the dimension of the image is
The size of the dimension of R3.
yes, which is
3.
3, right? If it's surjective, then it means that the image is the whole of R3, which means its dimension would be 3, right? But we have a theorem about the connection between the two. What is the dimension of the kernel plus the dimension of the image equal to?
The dimension of the range, or
Not the range, the domain. The domain.
Yeah.
Okay, it's 2. Contradiction. It could not possibly be an invertible function because one of the things here will not work. Which is the one that is more problematic?
In this case, the image.
The image, yeah. Actually, regardless of the kernel, the image cannot equal R3, and since the dimension of the kernel, which we don't care about, plus the dimension of the image ought to be 2, which means not just 2, ought to be the dimension of the domain. So the dimension of the image is always smaller or equal to the dimension of the domain, which means that every time that the domain is of smaller dimension than the range, then surely the function will not be surjective. Okay, it cannot be. But again, it's only because it's a linear function. It's not a matter of cardinality. If we would have opened it up to any function, then yeah, there are invertible functions from here to here, but not linear ones. Linear functions are matrices. They have specific properties that does not allow them to behave freely, let's just say. Okay. Similarly, if the dimension of the domain is larger than the dimension of the range, then the linear function t from V to W cannot be what?
Surjective?
Yeah, subtractive.
No,
If B is bigger,
if the domain is bigger,
Then it can be injective.
it cannot be injective. Why is that? Because otherwise, 0 plus the dimension of the image ought to be the dimension of the domain, which is strictly larger than the dimension of the image, because the dimension of the image is smaller or equal to the dimension of the range, which is strictly smaller for that dimension, which is strictly smaller than the dimension of the domain. And lastly, assume that the dimension of the domain equals to the dimension of the range. Does the linear function t from V to W, does this function has to be invertible? We've shown that if the dimension of the domain and the range are different than one another, the function cannot be invertible. That means that invertible matrices must be squared. But now I'm asking whether every function from a domain to a range, which are equal in size, in a sense, in their dimension, does the function has to be invertible? What do you say?
Because it's the dimension of the image just needs to be less than or equal to.
Yeah,
dimension of the-
it's equivalent to asking whether every square matrix is invertible. Obviously not. No. Any non-injective example will do. For example, take t from R squared to itself, such that t of xy is 0, 0. The zero function, it's obviously not invertible, right? But it's still from a domain to an image of the same size. Agreed? Now, I know I said lastly, but it wasn't lastly. Now, assume, because I'm still in the case that they are equal, but I'm asking something else. Now assume that the dimension of V is equal to the dimension of W, and T is injective? Does it has to be invertible? Why?
Because it's injective, it means that. You mean you want the matrix explanation or attempt or just function?
Whatever you like. I
So-
like them both.
So because it's injective, it has and it's square. The echelon form has a pivot point in every row. So that makes
Okay,
it
that's the matrix reasoning. You're right. And now the linear function explanation.
it has the same dimension, and we know that
We're right. We know that the dimension of the kernel plus the dimension of the image equals to the dimension of the domain, but our added assumption here is that it also equals the dimension of the range, right?
Mhm.
What do we know about the kernel here?
it's 0.
It's 0. The dimension is 0, right? So what is our conclusion? Thus, the dimension of the image must equal the dimension of the range, and so T is surjective. Actually, if the dimension of the domain is equal to the dimension of the range, then T is invertible if and only if T is surjective, if and only if T is injective. So that is something special about linear functions and matrices, not about functions in general, but in linear functions, yes, all these three are equivalent. But don't forget, if the dimension of the domain is equal to the dimension of the range, don't forget that. If they are not equal, then definitely the function is not invertible, whatever you do, right? One of the properties never holds. So this, I don't know, 20 minutes rant or 15 minutes rant shows you the main applications of the kernel and the image. Why do we study it? Right? These are the main applications. They help us know whether the function is injective, surjective, and whatnot, which are stuff that we are interested about in functions in general. And in linear function, they are very simple, and they all translate algebraically to matrices. Yes.
Why is dimker T? Why is the dimension of the kernel of T equal to 0?
Because I assume that T is injective. And that is the only theorem I actually proved today, that T is injective if and only if the dimension of the kernel is 0. It may have been when you stepped out after the recess, I might add. But
I was doing something important.
no, but seriously, I think actually I did it there. Here, look at it. This. Okay, so that's a proof. It's a readable proof, but it is important in the sense that this is the main reason to study kernels. right? Even later, forever it will take the option course of מבנים אלגבריים, we'll study about other algebraic structures, but almost all algebraic structures has kernels within them, and they always measure how much the function is injective. It's a general thing in math. But for us, we just study matrices and linear functions in this course. Any questions thus far? Okay, so we are done with the course. I skipped one theorem. I recalled it just after I said I was done with the course.
We're just.
I
about
leave it
done.
for linear algebra too. Thomas, I give you
The
the
responsibility of telling Gilad that
yes, exactly. That is the main thing we didn't even speak about.
What is it?
I'm saying משפט ההגדרה. I'll say it quickly by heart.
if you want to come next week and give an extra class.
Yeah. איפה זה רגע?
What a mess of a semester. On the like wars and whatever in the middle. It doesn't even let us finish linear algebra.
No, but we're almost finished. It's one theorem that I skipped. It's not that bad. Where the hell is it? Oh, it's within that. Okay. משפט ההגדרה. It basically says, I can word it in 2 seconds. If you have any base for a domain, you can choose where to send each element of the base, and there will be a linear function that does that, and there will be a unique linear function that does that. So again, v1 to vn is the basis for v. Choose randomly whatever you wish to send each element of the base. There is a linear function that does that, and there's only one. Okay, it's not for our test, but I simply told you this because sometimes we build function this way. We say, okay, I want this element to be sent here, I want this element to be sent to 0, and there is such a function that does that. So I think we use it in linear algebra too, but just in case I just saw it. So what will we do in the remaining 7 minutes? Now we will speak a little about the test. More importantly,
Revise for it.
what?
Okay.
No, I didn't
He
more.
asked if he has to study for it.
No, I said how to revise for it.
That is more important, but how to? You need to study the Word document. That's okay. Sometimes students think that the lectures are just background noise that has nothing to do with the course. But I will say something about that. I will build the test, and my purpose while building the test is making sure you understand what I try to teach you. So have that in mind. But what is even more important than that is having a prep lesson for the test. So first of all, when is the test?
Linear algebra 28th of July. Yeah, you remember I told you it's in the same week?
That's horrible. Yes, okay. So the prep session would be, and do you have any other tests other than me?
No, we have you twice.
No, but you don't have computer science?
Yeah.
No, that's what I mean.
I
It's a
have-
mix. It depends on who you're speaking to. In
The
class.
people that are doing Ulpan now have the test 2 days from now, And
That
we
I
have
don't care about. Do you have any tests?
the
We
23,
have ooh,
the object-oriented
Oh.
programming, the 23.
In the
so
23?
Yeah.
So you have 23, 28, and first. Yeah, you have 2 months of time for tests. Let's put all the tests
You know,
within a week.
you know what they say,
Haha.
they want to give us a lot of time for the model.
Yeah, but all the Moed bets, I bet,
but I'm sure.
would be, it was 12 words. I bet all the Moed bet, whatever. And will be on the same week, but just another week, right?
Yeah, probably. But also
It's like two people trying to move through a corridor. They both go to the right, and then they both go to the
I
left.
think I may be speaking, saying out of my ass. It's not financial the same class, right? But I think we all have מועדי ג' in theory.
Why? are you all
המדבר.
מילואימניקים?
לא, המדבר בגלל המלחמה בטילים בשטויות.
על המתווה? אתה מתכוון?
כן, כן.
I don't know, maybe. That's not for me to decide, so I don't care. Okay, so that's horrible. You said the 23, right?
Yeah.
How are you on Zoom on Friday morning, the 25th? Because I wish to give you like 2 days from the last trauma. Not good?
I mean, on Zoom, it's already like.
Oh, I don't mind coming here on Friday if you wish. I assumed you can't.
I think we can do it on Thursday.
The 24th?
Yeah, because like Friday is already like.
Wait, it depends what time.
Sammy, would you rather do it on a Friday?
It just depends what time on Thursday.
So
We don't care about Sammy.
let's
when are
let's
you
say
free?
Thursday on 3 o'clock. Is that good?
Sure.
Yeah, so from 3. So Thursday and 24, right in
How long is it gonna be?
from 3 to 6. Rap lesson. That's linear, right? Linear is the first.
Yeah.
Or linear. Okay.
The problem is how are we going to do it with calc?
Yeah, no, that's won't be solvable. And we talked about it. We'll cry a lot. I'll do a prep between linear and calc. I'll decide it in half an hour when we study calc, but it won't be ideal. בלשון המעטה. Okay, so Thursday between 3 to 6 we will meet for a prep session. Tomas, are you in connection with Mazkirot to ask for a room?
Yeah, sure.
I will be happy.
Why are you making Thomas ask?
Because Thomas is your representative. I always put it on the students. And so do you want you to be responsible? Okay.
Oh,
Please go ahead.
Yes. And so that's that.
Wait a second. I'll check again when the test is for the other stuff, so I don't get confused.
Okay.
Uh,
In the meantime, I will speak about the structure of the test. The test
Linear's on the
will
28 and T's on the first, right?
contain
Linear's on the 28 and T's on the first.
yeah.
4 questions. 30, 30, 30, and 20 points each. The first will include system of equations with a parameter.
I am image.
The second would be about complex numbers, including any other subject, which means I could do just complex numbers, system of equation with complex numbers, vector spaces with complex numbers, whatever. The third would be about matrix algebra and vector spaces. A lot about the P of A, R of A, and N of A, the spaces of a matrix. And the fourth is open for me to abuse you. Okay, it's open for me to choose. And that's like might be the more theoretical. My point in the test structure is that you will have like three rather technical questions, similar to stuff we did in class. Okay, the first three will contain problems that are similar, not exactly the same, but to problems we solved in class. And that also tells you how to prepare for the test. You need to go over the entire Word document, see every problem we solved, and say, this problem might just as well be on the test, and we need to know how to solve it. Everything, right? And these are the technical stuff. And the fourth question is more like general.
When you say, wait, can you go a bit further up? When you say the second would be about complex numbers, including any other subject, what does that actually mean?
I said it could be matrices with complex numbers, system of equations with complex numbers, a vector space over the field of complex numbers.
But okay. So in any case, it'll be applying our knowledge that we did with complex numbers.
Yeah,
to
usually. Yeah, just think that
vectors.
I think the easiest example is doing Gauss elimination and
With the-
using complex
right,
numbers,
right.
right?
So there would never, so there wouldn't be a question that was just like on its own, like.
No, it could be.
Like, oh yeah.
No, it could be. I could ask you find the roots or the fourth roots of a certain complex number. It could be as well. There will be a few safim. There will be a few parts for the question. Yes.
When you say that the first three are going to be more technical problems, does that mean that they're not proofs?
It doesn't, more technical doesn't mean there are not proofs at all. And when preparing for the exam, I urge you not to skip all proofs because it won't work. But like I said, there will be more technical. Okay, so take that with a grain of salt. Okay, yes.
How similar is it gonna be to the test from previous years, like the oldest study, I think it was 1, 2, and 4, like for specific exercise or problems, like will it be similar to those?
Yeah, from the Morim, right?
Whichever the link that you put in the doc.
Yeah, so I think it is rather close to what's in there. I look at it now, but I think it's rather close to what I described as well. Is it here, maybe? No. So Morashi. Simcha Morim. Rest of that. Linear. This link, right? Do you remember by any chance?
Probably.
I think it was this. And then I told you 2 here, 3, you see? It's rather close. So 3 and 4 here are like 3 in your class. Complex numbers won't be as such because these are actually matriculation question of complex numbers. You can solve it, it will be helpful, but it won't be as similar. But like I said, it will be similar to this, but this is similar to what I did in class. So you try making sure you know everything from class and use this to better prepare yourself, okay?
Is there any test you've done recently or a collection
No,
of
no,
tests?
no, this is the collection of tests. This is what we have.
What about the one on like the shared computer science Google Drive?
No,
It's, to be honest, the shared one is much harder than your will be, to be completely honest. Okay, we have a lot of tests here in linear algebra. They are much more complicated than I'm going to apply to you. You can solve them if you can, but these tests would be a bit easier. Oh, but I forgot something. Let me change it up for a bit, the structure of the test. I forgot.
Is there a question 5?
No, that definitely not. It's not. So, you know what? I'll leave it at that. The subject that I forgot is linear transformation. That's why I got it, because the regular test is mostly linear transformation, and that I will not do to you because we just learned it at the end, so it's not fair. So if I'll put linear and transformation, I'll put it in the 4th question. That's fine. And it's open for me to choose, so it's fine. So it might be technical, but still it will be a bit harder for you. But I urge you to study what we did today, for example. I won't be ashamed to put it on the 4th question, like finding the representative matrix. Even though it's technical, I consider it harder because we didn't have a lot of time to digest it. So yeah, that would be the structure of the test. So you can use any, it's not similar to the structure of the old tests, but it's for your own sake. It's different. Okay. So see you guys on calculus.